Today we're doing transformation of functions, and this is exercise 6.6 from Jack class book. So I want to point out first, before we do the first example, when we're talking about horizontal and vertical translations, there's a little list here. And as we know from quadratics or root graphs or truncus or hyperbola, any sort of graph, when our value is connected to the x, by the brackets or under the vinculum or in the root, in the square root sign, it means it goes in the opposite direction. So that negative h there is telling us that we're going h units to the right. So it's a horizontal translation. So if we're thinking about our x and y axes, and we have a point here, and we've got x f of x minus 2, that means we're going the positive direction by 2 units. So to say that's -1, then we'd be going to +1. -1 plus 2 would be +1. So we'd move the point over there. Of course, if we're going the opposite way, if it was a +2 here, then of course we would be going in the negative direction. The other type of translation is when we go up or down. So these are the values that are not connected to the x. So as it says here, we've got f of x, and then we've got a plus k there. That plus k is not connected to the x. It's not in brackets with the x. So if we had a parabola, that would be something like x squared minus 4. That would mean our parabola would be moving down by 4 units. If it was a +4, it would be going up by 4 units. The idea is that the value of k is not connected to the x. In a hyperbola, the thing that's connected to the x is underneath the vinculum with it, whereas the thing not connected to the x, or the value not connected to the x, the vertical shift, is not under the vinculum. So we want to think about whether something's connected to the x or not. So let's have a look what they want us to do. And they give us a diagram which has 3 points on it. And those 3 points are -2, 0, 0, 2, and 3, 1. And they're saying to sketch the graph of y equals f of x plus 1 using the image of these 3 points. So let's have a look. The image of these 3 points, well, I can say my y equals f of x equation. On that curve, I have the points -2, 0, I have 0, 2, and I have 3, 1. And now f of x plus 1, with the 1 in the brackets with the x, it's connected to the x. It goes in the opposite direction. So it means that each x value is going to go to the left by 1 unit. So left 1 unit. So it's going the opposite direction. So let's see. For my y equals f of x plus 1, well, each x value is going to go to the left one. So if we're at -2 and we go left, that's going to go to -3. The y value is going to be the same. At 0, it's going to go left by 1 unit. So it's going to go to -1. And of course 3 will go to 2. So see, the y values are not changing, just the x values going down by 1 or to the left by 1. So if we want to draw the image of each of those, well, over here I'm going to have this one at -1, 2. So horizontal shift. I'm going to have this at -3, 0. And I'm going to have this at 2, 1. So the y values are not changing, and then I would just draw my curve and it looks the same. My picture looks all right there. It's just shifting over in the negative direction by one unit. Let's have a look. Now we've got a different example, and now we're talking about reflections. So they give us a little list here, and we've got 2 types of reflections here. The first reflection is before the f of x. So this is the first place that we could have a negative. So in our equation, whereas if we look at the second place, we could have a negative. So in other words, within the function connected to the x, well, x comes before y in the alphabet. So that's quite an easy way to remember that the first reflection is a reflection about the y-axis. So in the x-axis. So x comes before y, reflection in the x-axis. Whereas our second reflection here is a reflection in the y-axis because it comes in the second place. So people get a little confused by that because the one that's connected to the x in brackets is a reflection in the y-axis. So let's see. We're considering the same graph that we had over here, and we can see that this negative is connected to the x. So it's the green one, a reflection in the y-axis. So what does this mean? Let's write those points out again. So y equals f of x, so our normal equation there, the one that's given. So those 3 points, neg 2, 0, 0, 2, and 3, 1. And then our new equation of y equals f of negative x. So this is a reflection in the y-axis, and what we know is when we reflect in the y-axis, we actually affect the x values. So these are going to affect the x values because it's a reflection in the y-axis. So our x values are going to be times by -1. So 2, 0. 0 is just still 0, neither positive or negative. And 3 becomes -3. So our y values are unaffected. And let's see why that will work. And a good way to think about it is with a parabola. And if I reflect it in the x-axis, across the x-axis, let's see what happens. Let's say we've got this point here, and I'm going to say that point there is going to be 2, 4. So if I flip this parabola upside down, which I will show underneath here, so I'm reflecting over the x-axis, but actually my x value of 2 is still 2. What changes here is my y value. It becomes -4. So you see, a reflection about the x-axis results in the y values changing. If we have a reflection about the y-axis, and I will use a root graph to show this. Actually, a root graph is quite convenient for showing both. So here's our, y equals square root of x. So if I reflect that over the y-axis, let's see, let's take a point. I'm going to take this one here, and let's say this is 4, 2. So then if I reflect it over the graph over the y-axis, this point is still going to have a y value of 2, but the x value is going to be -4. So that's going to be my new point. So a reflection about the x-axis affects your y values, a reflection about the y-axis affects your x values. So let's draw those points on. So we've got 2, 0. So let's put that here. And we've got 0, 2, which is still 0, 2, and we've got -3, 1. So -3, 1. And now we've got to reflect over the y-axis. It'll look like that. So we're taking it and we're flipping it over the y-axis there, reflection over the y-axis. So that's our new graph with new points there, and I should label those points actually. So 2, 0, 0, 2, that's already there, and -3, 1. So there would be my new graph. Next, we're talking about dilations, and this one's a little bit trickier. So when we've got, we usually would say from the x-axis. We can also say parallel to the y-axis, or, well, from the y-axis and parallel to the x-axis. But generally speaking, they use the words from the y-axis, from the x-axis. So I'll cross these out for the meantime, just so that we are not confused. And let's just see how that works. I think that the best way to illustrate the dilation is with a circle. Just a random circle. It doesn't matter if you know what the equation is or not. And let's see, if I have a point on that circle, let's say it's 2, 5, whatever it might be. And then If I say, well, now I'm going to dilate by a factor of 2 from the x-axis. So from the x-axis means it's moving away from the x-axis or coming closer to the x-axis. It's a dilation from the x-axis of a factor 2. So if I'm dilating factor 2, it means that I'm going to double the value. So what's going to happen is I'm going to double the y value because I'm moving from the x-axis. So it would become 210. So moving away from the x-axis by a factor of 2 or 3 or whatever it might be means you're getting further from the axis. When you dilate by a factor of half or something less than 1, you're getting closer to the x-axis. We can also think of it the same way for the y values, dilating from the, or not the y values, dilating from the y-axis. If I have this same point here, 2, 5, then I want to dilate by a factor of, say, 3 from the y-axis. So I'm moving from the y-axis. So what's going to happen is that my x value is going to change. My y value is going to stay the same. So it's going to be 6, 5 there if I dilate by a factor of 3, timesing all my x values by 3. So dilations and reflections, for that matter, they both affect the opposite. So a dilation from the x-axis affects y, dilation from the y-axis affects x. And I think it's best to ignore the parallel for the moment so you can get used to what the from means. Add back in the parallel once you're more sure. Okay, so let's see. They give us some rules there. Let's do the first one and we'll apply the rule that is relevant. For the graph given, so the same one we had, sketch the graph of y equals f of 2x. So let's see. F of 2x, this is this rule here. And what we do, it's 1 over whatever the value of a is. And in this case, it's 2. So if we want to write this down, this is a dilation factor half from the y-axis. So from the y-axis is going to affect the x values. So all the x values are going to be times by half. This is y equals f of x, and this is going to be y equals f of 2x. So we have negative 2, 0. We have 0, 2. And we have 3, 1. Okay, so all our x-axes are going to be, x values are going to be halved. So negative 2 becomes negative 1. Half of negative 2 is negative 1. Half of 0 is still just 0, so it's 0. Half of 3 is 3 on 2. Don't make a decimal, leave it as 3 on 2. So our new points there are going to be negative 1, 0. There it is. 0, 2. And 3 on 2, 1. So here. So let's draw that. And what we see here, it's all skinnier. Dilation of factor of half from the y-axis, it means you're moving closer to the y-axis, and indeed you are, because you see your graph moving inwards towards the y-axis. In the next video, we will do combined transformations, but for now, we'll just stop at the individual transformations.